Welcome back. Did you miss me? I thought you did. Alright, so we're on slide 27. Getting good here. It's getting good. Ice nuclei. So, ice as a nucleus above our heads. We're talking about a freezing point where we always know that 32 degrees is freezing, or 0 degrees centigrade. But we can have supercooled water as well. Water having a temperature below the melting point. Liquid water. And nonetheless, it's liquid. So that's called supercooled. In the clouds, we can have that because the pressures are lower. The pressures are different. Interesting, though. Ice crystals form is ice nuclei. It's the rare temperature is dependent upon the substance that's similar in shape to ice. It looks a lot like ice. It looks like a six-sided crystal, if you will. They become very active at temperatures of 4 degrees below centigrade. So super cooled. Once you get to -4, you can form these ice crystals or ice nuclei. When you get to -10 and all the way to -30 degrees centigrade, you can have saturation of the ice. Okay? And super cooled drops as well, so you can continue to have liquid water. You can start making more and more ice and eventually get saturated at that point, or you can get both. Below -30 degrees centigrade, clouds are composed mostly of ice crystals. Ice crystals, pretty much. Below -40, and at this point it really doesn't matter if you're on the centigrade scale or on the Fahrenheit scale. It doesn't matter. You can get spontaneous ice crystal formation, or in meteorology we call it spontaneous nucleation. And the direct deposition of the ice with no nuclei is present. In other words, at that temperature, it's just forming in the air and dumped on the ground. There's no condensation, if you will. There's no buildup. And then moving on, slide 28, we talk about the cooling the air to the dew point, or the frost point. It's called the diabatic process, or diabatic process. It's we're talking about the energy in the air mass, removing the energy in the air mass in order to achieve dew point or frost point. It's called the second law of thermodynamics, where the energy is always transferred from areas of high temperature toward areas of low temperature. Alright. Dew point is also rather interesting regarding fog in another way. The temperature of the ground is cooler than the temperature of the air. So you meet the dew point, the air temperature meets the dew point above the ground, and the ground is cooler. That should not be the case in the adiabatic process. But in the diabatic process, that's why we get the second law of thermodynamics to apply. Okay? Why fog occurs. We just take it for granted, but we live in the adiabatic process world. Slide 29. Cloud formation typically involves temperature changes with no exchange of energy. That's called an adiabatic process. It's the first law of thermodynamics. So rising air expands, as we typically expect, through an increasingly less dense atmosphere, causes a decrease in internal energy, and a corresponding temperature decrease. And typically a dry adiabatic lapse rate, which I mentioned to you last week, is about 1 degree drop centigrade per 100 meters or 1,000 feet. 5 degrees Fahrenheit every 1,000 feet. Okay, so about a degree centigrade every 100 feet, 100 meters. Okay, or a little over 5 degrees Fahrenheit every 1,000 feet. So we may actually reach a lifting condensation level, that height at which saturation occurs. So the dry, you have to think of it as dry, no moisture, but you can reach to a point in altitude where it becomes condensed, and parcels then cool at the saturated adiabatic lapse rate. So we cause a cooling at the saturated adiabatic lapse rate. As the particle of air rises, it begins to saturate, and as it begins to saturate, it begins to cool about every half a degree C every 100 meters, or 3.3 degrees Fahrenheit every 1,000 feet. Okay, so think about dry adiabatic lapse rate first. It seems to be a little easier to understand if you just think about the dry adiabatic lapse rate. Air, as it increases in altitude, decreases by 1 degree centigrade at every 100 meters. You can think of it like that. But if you have saturated air right at the surface, as the air mass increases in altitude, it decreases about half a degree C every 100 meters. It's warmer. I don't know if you get that, but moisture retains more energy. Moisture provides a higher heat capacity, so less energy is lost. Okay, the more moisture, the more energy, and that's going to take you down to where we start talking more and more about cyclones. Okay, so slide 30, the cooling of the air to the dew and frost point is also depicted in pictorially and graphically. I just wanted you to look over A, B, and C. This is the adiabatic process, opposite of diabatic process. So this is the first law of thermodynamics. And then slide 31 goes a little farther to show you about that rising air mass. We mentioned the adiabatic lapse rate and the saturation, the condensation lapse rate. But there's also the environmental lapse rate. So there's an overall decrease in air temperature with height. That's the environmental lapse rate. And that causes a change from place to place. It stems from the fact that the air located farther from the surface heating is typically cooler than that near the surface. Alright, so the environmental lapse rate is slightly different. You can see what the difference is in the picture. Okay, so slide 32. Again, dew. I'll reiterate it. Condensation on the surface. Second law of thermodynamics. It's often occurring in the early morning hours. The diabatic process is occurring. In other words, the sun's not there. The diabatic process is occurring when the warmer temperatures with moist air tends to transfer to the area with lower temperature. That's where you have dew. And you have long-range radiation that's being lost at night. Okay, and so that causes the surface to cool diabatically. Again, the second law of thermodynamics. Surface area becomes saturated and condensation forms on objects acting as condensation nuclei. So you walk out and your car is wet. You've been there. Or you have to turn on your windshield wipers. It's not even raining, but you have to turn on your windshield wipers and get the water off of the windshield. Frost, slide 33, is something I don't like. Some of you have been in these areas where you have a lot of frost. You know what it is. You know what it looks like. It's just like dew, except it forms when the surface temperatures fall below the freezing point of water vapor, below 0 or below 32. So that's when water vapor does not go into the liquid state. It goes from water vapor to solid. So that's called deposition. Alright. It's also can be referred to as white frost or hoarfrost. And then slide 34, you have frozen dew. So in other words, water vapor has transferred to liquid, condensed, normal dew formation through the diabatic process, but the drop in temperature occurred after the dew was set in, and so the dew freezes. So it's called frozen dew. This is a very dangerous situation on bridges when you're driving at early morning hours and dew sets in. The temperatures continue to drop at or below freezing. The ice can form and you don't even see the ice because it looks just like liquid. It doesn't look like ice. You know, ice looks more white. But because dew was setting in, the dew freezes from underneath. It starts from the surface up. You don't see it. So when you're driving over a bridge, it can be very dangerous and very slippery real fast. We call that black ice. So slide 35 is an example of dew, frost, and frozen dew. Slide 36, fog. Again, comes in 3 different ways, but typically it's when the air temperature is cooler than the dew point. And the ground surface is cooler than the air above. Okay, it forms a cloud on the ground. We have different types of fog: radiation fog, advection fog, and upslope fog. Distribution of fog can be thrown on a map, and you have those different types of fog are found throughout the United States. So as you go back to the slides, what advection is, and you can understand what I mean by advection. Fog. Radiation. Go back to the slides to understand what radiation means. I've already explained that to you, and you can pretty much understand what upslope means. Upslope fog. Upslope in the atmosphere. Okay. Remember, upslope has to do with the pressure gradient force. Now, slide 38. Formation and dissipation of cloud droplets. Oh, it's pretty interesting. It's when the sun's overhead. It's the adiabatic cooling of the rising air. First of all, starting that way. This is the beginning of talking about rain or precipitation. But dew points decrease as air rises at the shallow dew point lapse rate. So, in other words, there are varying rates as air rises in the air. But if air rises and it continues to be below the dew point also continues to drop as the air rises. So as long as the air mass stays below the dew point of the rising air, because the dew point's lowering as the air mass rises, and let's just say in this scenario that the air is typically at the dew point or lower as it rises. So that's called the dew point lapse rate, or the shallow dew point lapse rate of 0.2 degrees every 100 meters. So about 50 meters above this lifting condensation level, the condensation nuclei have condensed the water attached. It leads to additional growth of these drops over creation of new drops. So this is a very low cloud, very low clouds. It soon stops, leaving drops to slowly evaporate and sublimate, meaning these very low clouds still have a very great chance. They're not in the free atmosphere. They have a great chance to evaporate, become turbulent because of what? The Coriolis force. The Coriolis force can easily cause the water vapor that is, like I said, starting to look like a drop. Not look like a drop. It goes from water vapor all the way to, you guessed it, I'm sorry, it goes from liquid to vapor. Okay. It changes, skips a state of matter. Any questions about that? You feel more than happy. You can ask me later. What do you mean by sublimation again? Any questions like that, and I'll explain it to you. Okay, high humidity, slide 39. The higher the humidity, the more uncomfortable it is for you and me. So that's why we have a heat index, and if you've been in the military, you have wet bulb indexes, and it becomes a very dangerous situation if you're outside long periods of time with intense sunlight. We cool ourselves like a radiator. We sweat, and the sweat covers our body to cool the body. And why does it cool the body? The droplets of sweat evaporate. The evaporation causes a pretty quick cooling of the body, which is very a magic. It's magical. It's a benefit. Sweating is good. If you stop sweating, that's when it becomes bad, and the heat index is the problem. When the atmosphere has a high moisture content, the rate of evaporation is reduced. So if you ever have a high humidity, you can't evaporate that sweat. It's hard to do it, so you don't cool down. So high humidity can cause major problems. So the apparent temperature of the air increases, leading to heat-related health risks. So the humidity of the air, if you're outside a lot, becomes an issue, a health issue. Now, regarding atmospheric moisture and climate change, the Intergovernmental Panel on Climate Change, a policy-making panel formed by the United Nations in the 70s, they cite studies around the world that have been found increases in specific humidity. And remember, specific humidity is not relative humidity, but it is a part of specific humidity. Contributes to relative humidity, if you remember. Near the surface have been associated with increasing temperatures. All right, and over most oceanic areas, relative humidities. You got to really understand what they're talking about. Specific humidity, and now they're jumping to relative humidity. They've remained fairly constant. So over the ocean, relative humidities remain constant, as increasing water vapor contents have been offset by increases in the saturation. Specific humidity. So I want you to go back to your slides and notice that I have jumped around. I started off in the first bullet talking about specific humidity. then relative humidity, then saturation specific humidity. What am I trying to say here, and does it make sense? Is it oranges to oranges? Then over some land areas, increases in specific humidity have been more than offset by increases in the saturation levels, leading to locally unchanged or slightly reduced relative humidities. So, I leave that with you. It's a quandary to talk about climate change. These three bullets are looking at a long period of time, or that's the intent. We cannot talk about the weather. We have to talk about the climate regarding these three bullets, and that's the quandary. What can we deduce simply by looking at atmospheric moisture? Well, the IPCC has come up with some observations and conclusions, and we are now working on globally putting them into law. Anthropogenic causes for climate change. So it's something that we'll continue to discuss in our class. Alright, well, that ends all of Chapter 5's lectures and Chapter 4's lectures for week 3. I hope that this has been helpful in the video lectures, because it helps you by not traveling to the class, being that it's a hybrid class. However, if you have any questions, you are welcome to email me, and I will respond, as many of you have already realized that. I will get back with you as quick as possible, relatively quick. Okay. I do have one announcement to make before you hang up on me. I will be out of town Friday, Saturday, and back Sunday. I'm going to a remote location with my family, hiking, looking at some of the most precious geologic resources in West Texas. My cell phone will not be that great out there, and I will be camping. I won't have Wi-Fi. So, just wanted to let you know. So if you have any questions, and you send me an email, I will not respond during that time as well. If my cell phone works, I will respond as best I can. However, just be aware of that, and I'll get to my emails during that time as best I can. Okay, thank you, and have a great week 3.